So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. And that theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever. And it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, stretch, stretch. And then it slows down and stops in little patches. And each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs. And that's called the inflationary multiverse. And it answers some neat questions, because if you say, why is our universe the way that it is? Why are the laws of nature such that life can exist, for example? Well, the answer might be that all possible combinations of all the laws of nature exist in the inflationary multiverse. So then it's not surprising there are universes that permits things like us to exist, because every possible universe exists in the inflationary multiverse. And that's a well-supported theory. It's a theory. So this is not the same as saying there was a Big Bang, which we know. This is kind of, what's a theory? It's a guess, basically. But it is a theory that in its simplest form has made predictions that have subsequently been verified. And we could go on then. There's the so-called many worlds interpretation of quantum mechanics, which is more kind of Marvel film kind of multiverse, where, so quantum mechanics it's a probabilistic theory. So imagine a quantum coin, I call it. And the quantum coin it doesn't have to be heads or tails, it can be heads and tails. So it can be mixed up, it can be both heads and tails at the same time. You might have heard of Schrodinger's cat, which is a cat in a box, and it's both alive and dead until you observe it or interact with it in some way, and then you find out which one it is. But before you looked at it, or before you interacted with it, it was both. Yeah, I mean, so I say sometimes in my live shows, it's kind of a joke, right? So I'm not insulting philosophers here, but I say there's only one interesting question in philosophy, right? And I don't really mean it, but I think it sounds funny. So the interesting question is, what does it mean to live a finite, fragile life in an infinite, eternal universe? So that's not that funny, right? It's a good question. What does it mean to live a finite, fragile life in an infinite, eternal universe? And I think the answer is that, sort of paradoxically, whilst we are definitely physically insignificant, I've just said, that the Earth is one star around the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of the universe, right? So we're definitely small, and you can't argue with that. We're just specks of dust. But if you think about what we are, so everybody, me and you, everybody, we're just collections of atoms, right? Some of them are as old as time, pretty much, and some of them were the other ones. Everything else, other than the hydrogen in our bodies, was made in stars, right? So we're all cooked over billions of years. And we're in this pattern that can think. So suddenly, as the great Carl Sagan said, you have a means by which the universe understands and explores itself, which is us. And that sounds unlikely when you put it like that, that you can have a few things that were cooked in the hearts of stars, you stick them together in a pattern, and suddenly it has some ideas and starts writing music and art and things. That's quite difficult to comprehend, right? But that happened here. We know that because we're sat here having a conversation. And so the question then becomes, well, on how many other worlds did that happen? And that's where I think the value can come in, because it's a reasonable guess, and it's just a guess, right? But it's reasonable. You can make the argument that there aren't any other worlds where this happened, certainly in our galaxy. So it could be that this planet, notwithstanding its physical insignificance, is the only place where anything thinks, right? For millions of light years in every direction. And suddenly, therefore, you end up considering this planet as being the most valuable place in the local universe, notwithstanding the fact that it's small. And that idea, it's not just a complete random guess, by the way. We've had a bit of a look. Astronomers have pointed radio telescopes up at the stars for a while, 50 years or more now, and heard nothing. We've seen no evidence of any civilizations out there beyond Earth, and that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that, and the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from a single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. That is a really long time. If you say, that's an unbroken chain of life on a little piece of rock in a violent universe, and that chain was not cut for 4 billion years in order to get us. And that might be a big ask, right? We live in a really violent universe. You look at the Milky Way and you look at that arc of stars across the sky, 400 billion suns. All there will be up there at best is slime. Just slime, nothing, right? And I think that's a reasonable guess. That's where I start from. I mean, I wouldn't be surprised if that's wrong. Then you go, okay, good, well, fine. But at the moment, it looks like there isn't anything else other than slime. We haven't even discovered slime, by the way, yet. We're still in the position where we've not seen anything, not even a single cell on Mars or the moons of Jupiter or somewhere like that. So at the moment, we are alone, as far as we can tell. Enrico Fermi is one of the great physicists, legendary Italian physicist, who laid many of the foundations of modern 20th century physics, so-called Fermi-Dirac statistics and all sorts of things. If you do a degree in physics, then you will spend a lot of time revising equations and theories that Fermi did. One of the great legends. The Fermi Paradox is it's probably the thing he spent least time on, actually. It's almost one throwaway remark that he delivered. And the question is, where are they? By they, I mean aliens. The heart of the Fermi Paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi Paradox, at its heart, is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or the great, I would say the intellectual value of the Fermi Paradox. So if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi Paradox, this is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago, but it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi Paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wiped out the large dinosaurs, there's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say it's a property of a solar system. It's not really just a property of the planet. It's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi Paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi Paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, let's say 20 million, 30 million, 40 million light years away, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Now, perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. What is the best bit of evidence for alien life? We don't have any evidence for alien life, is the answer. So in the past, so we've landed missions on Mars, for example, the Viking missions in the 1970s, there was some suggestion that there might be some chemical reactions that looked a bit like life, and then it turned out that it probably wasn't, because it's very difficult to distinguish geology and chemistry from biology when you don't know what the kind of biology is that you're looking for. And so the answer is we don't have any evidence of alien life, of life beyond Earth, but we're looking. It's, as I said at the start, it's one of the questions I really want to know, and I think we might answer very soon. Obviously, if there isn't any, we'll never answer the question, because we can never say certain. I'll tell you why, actually. We've been measuring, so how many other planets are there, is the first question. Well, 20 years ago, just over 20 years ago, we didn't know of any outside the solar system. Now we know that virtually every star in the sky has a planetary system around it, at least one planet. We suspect from measurements from a telescope called the Kepler Space Telescope that there are maybe 20 billion Earth-like planets in the Milky Way galaxy. We've discovered close on, I think, confirmed planets, about 1,700 planets that we've actually confirmed exist. And so essentially everywhere we look, every star we look at appears to probably has a planetary system. So there are a lot of planets. So life on them, how could we detect that? Well, we're at the level now where with our telescopes we can look at the light. So you imagine a star and you imagine a planet passing across the surface of the star. Then the light, some of the light from the star passes through the atmosphere of the planet on its way to our telescopes. And that allows us to analyse, to chemically analyse the planet's atmosphere. So we can look for signs of life in the atmosphere. An example on Earth would be oxygen. So the oxygen in Earth's atmosphere, virtually all of it, comes from photosynthesis. Without photosynthesis, we wouldn't have an oxygen atmosphere. So if you see a planet with an atmosphere filled with gaseous oxygen, then you might be pretty confident that there's photosynthesis on that planet. You might even, some of my astronomer friends speculate that what would happen if you found industrial pollutants in the atmosphere of a planet? You could do it. Things like CFCs, these things that we manufacture here that are not natural. You could find signs of non-natural elements, not only produced by plants, but produced by a civilization, even. You could imagine that. So we have the chance, at least now, of analysing the atmospheres of these planets to look for life on them. As I mentioned earlier, the life on Mars, we're looking for that very seriously. Why? Because we think there's a chance that certainly a chance that it did exist at some point in the past, because we know water flowed over the surface of Mars. But we also strongly suspect that there's water below the surface of Mars now. And so any microbes that evolved perhaps many billions of years ago could have survived subsurface. So we may find life on Mars. So I think that's potentially one of the great discoveries. That it's a guess again, it's not a particularly scientific thing to say. The reason we build big spacecraft to go and land on Mars is because we want to look. So we don't know. If we knew, we wouldn't go and build a spacecraft to go and have a look. Yeah. So, but yeah, I think it's very exciting actually at the moment now. Because the thing is, like we said, the flip side of this is there are loads of planets out there. And there's been loads of time. This has got a name, actually. It's called the Fermi Paradox, after someone called Enrico Fermi, a great Italian physicist, who asked this very simple question, which is, where are they? Because given the number of planets, given the number of stars, and given the amount of time that there's been in this galaxy for complex life to emerge. So part of the evidence, part of the great conundrum here is that, so on the one side, yes, we've got the history of life on Earth, which says that we took a long time to emerge. And so it looked quite like an unlikely process. On the other side, you've got all this real estate, which we're discovering every day, all these places where life could emerge. And you have this, so if you think about where we could go, what could we become as a civilization? So already we've got, you know, what SpaceX are doing. I think today they're launching 2 Falcon 9s, aren't they? You've got reusable rockets. We are becoming a spacefaring civilization now very quickly. So give us, you know, it's 100 years ago that the Wright brothers flew for the first time. 60 years after that, we went to the moon, and now we're becoming a true spacefaring civilization. Give us 1,000 years. Give us 1,000 years when we don't destroy ourselves or do anything stupid. I'm sure we're going to be on Mars, we're going to be on the moon, we're going to be thinking about perhaps taking our first steps out to the stars. Give us 1,000,000 years, 1 million from now. If we survive, we should be an interstellar civilization. So we should be the ones that are going out into the galaxy. You would think that. There's nothing in the laws of physics that says you can't do it. Now, 1 million years, the galaxy has been around for the age of the universe, 12, 13 billion years. It only takes a few civilizations to have evolved a bit ahead of us. 1 million years. Give it, let's say 10, well, let's say 1 billion years. 1 billion years, it's still nothing. You get some civilizations that evolved 1 billion years before us. Why are they not there? Why can't we see them? Well, exactly. So, and then people start saying, well, maybe there's a finite life that all civilizations have. Maybe they destroy themselves. Maybe they don't become spacefaring civilizations. It's Elon Musk's argument. But when you ask him, why do you want to go to Mars? He says, because I don't want the human race to destroy itself.
Yes.
So it's his central argument. Because you can make a very strong argument that we should see the thing. It should be like Star Wars. Right, it should be crawling